Today we're going to take a peek at exponential functions, and we're going to take a look at how to graph them as well as how to solve some of them. So we start out with basically a parent function, and our parent function is an exponential of the form cx to the a. All exponentials will be of this form, and this is your basic function where your base value, 3 is a base. We call that a is equal to the base. And then your exponent x is obviously your variable, outputs y. So what I like to do on these is I just, first time through, I'll take and plug and chug. So let's pick some positives like 0, 1, and 2, and some negatives like 0 or negative 1 and negative 2. I plug in 2, 3 squared is 9, plug in 1, 3 to the first is 3, plug in 0, anything to the 0 power is 1. 3 to the negative 1, that's like taking the reciprocal, so that's 1/3, and then finally 1/9. So if I go ahead and graph those, here's 0, 1, 0, 3, 6, 9, 1/3, 1/9. So you can see this exponential function rises quite quickly, like so. And it levels out. What power of a positive number will ever equal a negative number? None. So what happens in all of these exponentials is we're going to get some horizontal asymptote. And in this case, our asymptote is at y equals 0. Now, the range for this and the domain for this we can see by just looking at the graph. You notice that the blue line will go on forever to the left, and in theory, even though it's going up very high, it continues to move over to the right as well. So your domain for these is all reals. And then the range, this never goes below this horizontal axis of y equals 0, and it'll never actually touch y equals 0 either. So our range is y is greater than 0. Let's move on to the next. So we've already gone through our transformations, and a f of x minus h over b plus k. This works for any kind of function, including these exponentials. So we notice here, negative 5 is our h value, and our k value is negative 2. Which means this moves over and down. So what I'm going to do is move over 5, 1, 2, 3, 4, 5, down 2, and I'm going to create this fictional set of axes here. And then I'm going to graph my parent function, since there is no a value. I'm going to graph my parent function from that point. And my parent function is just 2 to the x. So if I take a look at some values here, negative 2, negative 1, 0, 1, and 2, I know that at 2 I have 4, 2, 1, 1/2, 1/4. And I'll do all that graphing from this new point down here. So 0, 1 puts me at this point. 1, 2 puts me at this point. 2, 4 up here. Negative 1 1/2, negative 1 1/4. And I'm going to go through and just make sure I check this as well. So I'm going to pick an actual point somewhere on this graph. This is a good one right here. It's easy to see, so it's negative 3 and 2. And I'll plug it into this function here to make sure it works. So I have 2 to the negative 3 plus 5 power minus 2. So this is 2 squared, which is 4, minus 2 is equal to 2, and that checks. So I've done it correctly. Now let's look at the domain and range. Again, this seems to take and move all the way to the left, and it keeps going to the right, so this will be all reals again. Before I do the range, let's take a look at an asymptote. You can see that it'll never go below this dotted line here. So it appears my asymptote is at y equals -2, and my range is always above that, so y is greater than -2 will be my range.
So here's another example where we're going to work with a special constant in mathematics called e, which is sometimes known as the natural base. And e is a number that's equivalent to 2.718. All right, and it acts much like the constant like pi, which is 3.14-ish. All right, and it's a variable that has a specific numerical value. And we're going to graph the function y equals negative e to the x minus 3, very similar to the way we've already approached these graphs. First, we'll identify our values. A in this case is -1. H in this case is 3. The k value is 0. And there's no b value. So because we have an a value of -1, that's a y multiplier of -1. Now, to calculate the parent function of y equals e to the x, we'd actually have to use our calculator, which for the most part defeats the purpose of graphing by hand if we're using a calculator to do it. But let's just go through. We'll do what we've done with all of our other examples. Use some small numbers like -2, -1, 0, 1, and 2. 0 is actually the easiest number to pop into this function. So we go e to the 0. Anything to the 0 power is 1. E to the first is just e, so that's 2.7. If I go e to the second, again, I'm going to plug that into my calculator, which is approximately 7.4. E to the -1, which is 1 over e, is about 0.36. All right, and e to the -2 is about 0.13. And then we're going to take and multiply those y values by a -1, thus giving me -0.13, -0.36, -1, -2.7, and -7.4. And what we're going to do is we're going to graph this pattern from our translated origin. And our translated origin is our hk value, which in this case is 3, 0. So I move over to 3, up 0, and put my little crosshairs, if you will, for our translated origin. And now I'm going to graph these x's and these y's from this new origin. So in doing so, I go over 0, down 1, puts me here. I go over 1, down 2.7, right around here. Go over 2, down 7.4, 3, 1, 2, 3, 6, 7.4-ish. Back 1, down 0.36. Back 2, down 0.13. So if I were to draw this, connect the dots, looks something like this, moving through here. And once again, we've basically got an asymptote on this horizontal right here that this line will approach. So therefore we can now go ahead and write the domain, since it continues on forever, -x and +x. That's all real numbers. Our range, since it will never hit 0, is y is strictly less than 0. And our horizontal asymptote, as we said, is y equals 0.
All right, now we're going to solve some exponentials. Let's look at a basic example. If I have something like 2 to the x is equal to 2 to the 7th, I'm not trying to insult your intelligence, but what would be the x value? Well, if these base values are the same, 2 and 2, then these exponents would have to be equal. So x obviously would equal 7 in this case. Same principle here, my two base values are the same, but I have different exponents. Well, if this is going to be 5 to some power, and we have two unknown powers, but the quantities have to be equal, then these powers must be equal. So I can basically drop the bases out and set x plus 1 equal to 6x plus 11. Again, this is only when your base values are the same. So I solve and I get 5x equals negative 10, and negative 2 is equal to x. So now in the next two cases, our base values aren't the same. However, we can make one of these numbers look like the other without changing its value. Now a lot of people will always go, well, 3 squared is 9. But if I make this 3 squared, I'm changing the value of 3. Whereas if I say, well, hey, 9 is 3 squared, I haven't changed the value of 9. And that's raised to the x plus 1 is equal to 3 to the 4x plus 5. Now I have properties of exponents that say if I have a power raised to a power, I can multiply those powers. So this is just 3 to the 2x plus 2 is equal to 3 to the 4x plus 5. And now you'll notice my bases are the same, so I can drop the bases out and set the two powers equal to each other and go ahead and solve that simple linear equation. So I have 2x equaling negative 3, and negative 3 halves is going to be equal to x. Likewise over here, I'm going to try to make one of these look like another, or maybe both of them look like something else, which is the case in this situation. 4 is easily expressed as a power of 2, that's just 2 squared, and that's raised to the 2x power. If I want to make 1/2 a power of 2, that's simply 2 to the negative 1 power. Remember, those negative powers take the reciprocal of its base. So that's to the 1 minus 2x power. Again, I have power quantities raised to another power, so I'm going to multiply powers. That's 2 to the 4x is equal to 2 to the 2x minus 1, distributing the negative 1 through. Again, I can drop the bases out, so that's 4x equals 2x minus 1, 2x equals negative 1, and x is equal to negative 1/2. Alright, so the next thing we're going to do is we're going to determine if we've got a linear or an exponential pattern. Alright, and it's basically the case that if the rate of change, which means the slope, right, we know that, if the slope from point to point is constant, it's linear. If the ratio of consecutive outputs, this is new, is constant, then it's an exponential function. So let's take a look and calculate the slope from point to point. I'll put m right here. So the slope in this case, between these two numbers, we're going to take the difference of y's minus the difference of x's. So in this case, we have 2 over 2, which is equal to 1. Find the slope in this case, 2 over 2, which is 1. This case, 2 over 2, which is 1. And in this case, 2 over 2, which is 1. So this appears to have a constant slope. And when we have a constant slope, we know that this is a linear function. Or constant rate of change. And if I were to graph those things, you could easily see, kind of with the naked eye, that that's going to be the case. Something of this nature. So it's going to appear to rise like this. Now, again, looking at the naked eye of this chart here, we'll see this appears to not be linear. If I go 0, 3, 1, 6, 2, 12, 4, 48. It's off the page. It appears to be rising quite sharply. So it could be exponential, but we have to make sure that this ratio of constant or consecutive outputs is constant. Let's go through and calculate slopes first. M is basically 3 over 1. The slope here is 6 over 1. So that's equal to 3, 6. Slope here is 12 over 1. So we got 12, etc., etc., etc. This guy is going to be 24 over 1, which is 24. Now, when we talk about consecutive output ratios, ratio consecutive, right? We're going to basically take and find the ratio of all the y's to each other. So in this case, what I have is I have 6 over 3 for the first one, which is 2. 12 over 6 for the second one, which is 2. 24 over 12 for the third one, which is 2. 48 over 24 for the next one, which is 2. And you can see that the ratio of consecutive outputs being y, is constant. So this is exponential. And that's how you tell if something's linear or exponential as far as their pattern goes without having to graph it. So that should get you through today's lesson. And do your Mind Math Lab, write the summary, and we'll talk about this more tomorrow.